A Class II cavity preparation is a strict microengineering problem. Amalgam is a heavy, brittle metal, and the host tooth is a living, complex structure. Every dimension cut into the dentin serves a specific purpose in balancing the physical weakness of the restorative material against the structural limits of the tooth. Deconstructing a flawless preparation backwards reveals the exact histological and physical laws governing operative dentistry. Mastering these spatial modes shifts the focus from simple memorization toward a predictive clinical engineering approach. This diagram shows an occlusal view of a mandibular first molar. The starting outline is dictated directly by the tooth's topographical map of grooves and cusps. On this molar, the boundary traces the central, buccal, and lingual grooves, creating a precise plus-shaped cavity outline. This maxillary first molar features a raised oblique ridge running diagonally from the mesiolingual to the disto-buccal cusp. To protect it, the preparation cannot cross it. Instead, the outline is split into two distinct shapes, a mesial C-shape and a distal comma shape. The strict exception to this rule occurs when the remaining sound tooth structure between two cavities measures less than 0.5 millimeters. Under that threshold, the remaining wall will fracture under load, and the two cavities must be merged into one. The external outline is never a freehand drawing. It is a predetermined path dictated entirely by existing anatomical ridges and structural tolerances. Once the surface boundary is set, we establish the internal vertical dimensions. This cross-section illustrates the rule for occlusal width. The preparation must not exceed 1/4 of the horizontal distance between opposing cusp tips. Clinically, this yields a strict measurement, roughly 1.5 millimeters in the central groove, narrowing to about 1 millimeter in the buccal and lingual extensions. Moving vertically, the dentino-enamel junction, or DEJ, is the critical biological landmark for establishing depth. The pulpal floor must breach the DEJ and terminate exactly 0.2 to 0.8 millimeters into the underlying dentin. Factoring in the thickness of outer enamel, this internal drop equates to roughly 1.5 millimeters of total depth measured from the top occlusal surface. These exact boundaries provide enough volume to pack the restorative material while preventing catastrophic hollowing of the tooth's structural core. The preparation then extends down between the adjacent teeth, forming the proximal box and terminating at the flat gingival seat. This magnified diagram of the gingival seat reveals a distinct histological challenge. Here, microscopic enamel rods angle sharply downward. Cutting a flat angle leaves the tops of these rods unsupported. When occlusal force strikes, the exposed ends readily fracture off. We resolve this by applying a precise 15 to 20 degree bevel to the gingival margin. This sweeps away the fragile ends, leaving only rods fully anchored into the solid dentin wall. To maintain adequate space, the proximal margins must also drop past the contact area, achieving exactly 0.5 millimeters of clearance from the adjacent tooth. The gingival bevel operates as a strict geometric defense against microscopic structural collapse. While the preparation protects the tooth's histology, it must simultaneously protect the physics of the amalgam restoration. The axiopulpal line angle, the internal corner connecting the horizontal floor to the vertical wall, is the primary stress concentration zone inside the tooth. Under biting pressure, a sharp internal corner causes mechanical forces to spike, rapidly driving fractures through the metallic filling. This internal line angle must be rounded to dissipate the stress across a wider surface area and to increase the bulk thickness of the amalgam. This diagram of the external cavosurface margin, the exact junction where the preparation meets the outer enamel, shows the opposite requirement. Here, a protractor measures a strict 90-degree butt joint. Amalgam filling material has extremely low edge strength. Beveling this external boundary to anything less than 80 or 90 degrees creates thin, brittle margins that will quickly chip under load. Internal rounding prevents core fracture, while external 90-degree joints prevent marginal chipping. With the geometric boundaries established, the final stage is the biological excavation of carious tissue. This comparative illustration maps the two layers of decay. On the left is infected dentin, the outermost layer. It has a soft, mushy texture, irreversibly denatured collagen, and is packed with bacteria. Because infected dentin is incapable of remineralization, it must be aggressively removed. Beneath it lies the affected dentin. It is dark brown and leathery. Its collagen is only reversibly denatured, and it contains no bacteria. Aggressive overpreparation into this layer is a clinical failure. Preserving affected dentin allows the tissue to remineralize and heal. A standard Class II cavity preparation operates within a complete spatial matrix, governed by exactly 11 line angles and 6 point angles. This rotating 3D model demonstrates how these individual measurements integrate to mediate tension. We see the external 90-degree butt joint, the 15-degree gingival bevel, and the rounded axial pulpal line angle. Bevels specifically manage the histological limits of enamel, while butt joints manage the physical limits of the amalgam. Recognizing this interconnected system provides a logical anchor for the specific dimensions, turning a list of measurements into a functional blueprint for the tooth. A precise cavity preparation is the ultimate expression of biomechanical harmony between host biology and synthetic engineering.